Clamp-on Ultrasonic flow measurement. My name is Tom Michalowski, and I am the Global Product Manager for Clamp-on Ultrasonic and Vortex flow meters with General Electric. I've been with General Electric and Panametrics for over 17 years with experience in flow, gas, and moisture measurement. Without further ado, let's begin. It is amazing to see how ultrasound is used every day. In nature, bats use ultrasound and echolocation to determine the location of insects in hunting. They create sound and determine location by the reflection time delay and relative intensity. Similar to bats, submarines use both passive and active sonar to determine location of objects. Ultrasound is used to image internal body parts such as tendons, muscle, and other internal organs, but is commonly known for viewing unborn babies. Non-destructive testing uses ultrasound to inspect for flaws in materials, validation of material thickness, and as an alternative to radiography for inspecting welded joints. In fact, GE has a separate inspection technology business that utilizes this technology. I'll let them explain it to you in a separate webinar. Ultrasound is used in chemical process cleaning of jewelry, optics, dental instrumentation, and other electronic parts by generating microbubbles in cleaning solutions to remove undesired contamination. Finally, ultrasound is used today to determine the flow in pipes. Before we go too far, let's start with the basics. What is ultrasound? Ultrasound is a sound wave with a frequency greater than 20 kilohertz. From your chemistry and physics days, frequency is defined as the number of occurrences over a specific unit of time. We typically think of a wave with a number of cycles per second, commonly referred to as a hertz. As a reference point, the typical audio range is 20 hertz to 20 kilohertz. Subsonic waves are 0 to 20 hertz. Ultrasonic waves are above 20 kilohertz, as we have already pointed out. When discussing ultrasound, an important side note is that different materials support different frequencies. Typically, a frequency of greater than 1 megahertz is used for solids. 250 kilohertz to 5 megahertz is used for liquids, and 20 kilohertz to 200 kilohertz are used for gases. The final application of a specific frequency to media will depend on many factors such as acoustic attenuation or absorption. Now that we understand ultrasound, how do we generate an ultrasonic wave for instrumentation? Well, we use a transducer. A transducer is made of a substance that will convert electric energy into mechanical energy or vice versa. When you want to transmit an ultrasonic signal, electric energy is applied to a crystal which stresses the crystal. Once the electrical energy is removed, the crystal relaxes and converts the energy into a sound wave. This is commonly referred to as the piezoelectric effect. The same effect can happen in the reverse direction, which the transducer absorbs the mechanical sound wave and converts it into electric energy. Therefore, a transducer can act as either a transmitter, receiver, or both. Now that we understand ultrasound and how ultrasound is created, the next logical step is to see how it applies to flow meters and flow measurements. There are several methods of ultrasonic flow measurement in the market today. Transit time is the most popular method for measuring flow with an ultrasonic flow meter. With a transit time flow meter, two transmitters are mounted on opposite sides at an angle so that one transducer is upstream of the flow and the other transducer is downstream of the flow. The transducers act as a pair and both transmit and receive ultrasonic signals. However, when there is flow in the pipe, the signal from the downstream transducer will slow down as is going against the process fluid to the upstream transducer. The opposite occurs as the signal from the upstream transducer will speed up going with the process fluid to the downstream transducer. This time difference is proportional to velocity. Doppler, was the original method for measuring flow with an ultrasonic flow meter and is typically only used in applications with very high amounts of solids or gases in a liquid medium. With a Doppler or Doppler shift meter, an ultrasonic signal is sent from a transducer and the signal bounces off a sonically reflective material such as a bubble. Assuming that the material is traveling at the same speed as the fluid, the returning frequency will be different based on the velocity of the sonic reflected material. Last, correlation tag is a method of measuring flow with an ultrasonic flow meter. With a correlation tag meter, two pairs of transducers are used, and the pair of transducers act exclusively as a transmitter and receiver to generate a tag path. Each path detects the disturbance in the flow caused by naturally formed vortices in the flow. By tracking the time it takes for each of these disturbances to get from one path to the second path, and knowing the distance between the two paths, the velocity can be calculated. Beyond the measurement techniques of transit time, Doppler, and correlation tag, ultrasonic meters can be applied by either wetted or clamp-on transducers. With wetted transducers, the transducers or transducer system directly touches the process fluid. With these systems, the transducers are typically installed with a meter body that matches the process piping material, pipe schedule, and flange rating. Wetted transducers can also be installed in special situations with either a cold or hot tap kit. Clamp-on transducers are mounted to the outside of the pipe using a clamping fixture with a strapping mechanism. Also, as shown in the clamp-on transit time picture, transducers can be mounted on either the same or opposite side. If mounted on the same side as shown, the signal bounces off the pipe wall and travels to the other transducer. In this picture, it would be considered a two-traverse installation or a V-bounce. Since transit time ultrasonic flow meters are the most common in the industry today, it makes sense to dive a little deeper into this method. As discussed, transit time uses at least one pair of transducers mounted at an angle from each other to measure flow. With flow in the pipe, the time that it takes to travel from the downstream transducer to the upstream transducer, shown as T up, will be greater than the time it takes to go from the upstream transducer to the downstream transducer, as shown as T down. The common analogy for transit time flow meters is a person canoeing on a river. It is faster and easier to paddle with the flow than against the flow. Beyond precisely measuring the transit time, accurate placement of the transducer is critical to the velocity measurement. The path length from transducer face to the transducer face and the axial length is just as important as the time measurement. Using transit time flow measurements has advantages since it can measure zero flow. With no flow, transit time up will be the same as transit time down. Also with transit time measurement, the sound speed of the fluid is calculated and can be used for diagnostics and troubleshooting. Sound speed is the time a sound wave takes to propagate through a fluid. It is a natural property of any fluid and is mostly a function of temperature. By knowing the fluid, the insulation accuracy can be validated with sound speed. Also, an ultrasonic meter can track and trend a fluid sound speed for changes in process conditions or process media. Flow meter users choose ultrasonic flow meters for many reasons due to their natural advantages. A common choice for selecting an ultrasonic flow meter is that these types of meters do not drift or require periodic calibration. Therefore, an ultrasonic flow meter is very repeatable over the life of the product for process control optimization and efficiency. Also, no calibration or periodic maintenance is required once installed. Calibration maintenance translates into both extra cost and extra time to maintain the flow meter. With ultrasonic flow meters, the sensors do not cause a pressure drop and do not waste energy. Ultrasonic meters also do not cause restriction in the pipe, require filters or strainers, or have any moving parts. Contamination within the fluid and pipe could damage other flow meter technologies, causing either drifting measurement, periodic calibration, or worst case, placement of meters. Ultrasonic meters are bidirectional, which can save you money if your process flows in both directions, such as a loading and unloading type application. Finally, the flow measurement is independent of temperature, pressure, viscosity, and conductivity. Therefore, an ultrasonic flow meter can be set up for different fluids and process conditions without significant impact to the measurement and process control. There are many different types of ultrasonic flow meters in the market today. For wetted or inline meters, we have high-accuracy custody transfer and allocation meters for both gas and liquid. We also have high-temperature inline flow meters for applications such as heater feed flows in delayed cokers with temperatures up to 1,000 degrees Fahrenheit. For permanent clamp-on meters, we have hazardous area meters at loading docks to monitor the fluid flow of different liquid media during loading and unloading stages. We also have clamp-on water meters used to allocate water flow from rivers as part of regional water management programs. For portable clamp-on meters, liquid and gas meters are available for almost any application. The best advantages for a clamp-on ultrasonic meter is that it is non-invasive and can be installed or removed without shutting down your process. Therefore, they are ideal for troubleshooting existing installation, validating another flow meter that is already installed, monitoring a new location, or used as a temporary permanent meter. Clamp-on meters have even more advantages to offer flow meter users. They can be installed on either new or existing pipes, which make them very convenient to install at any time versus other wetted technologies. Clamp-on meters are installed on the outside of pipes and do not require extra welding or additional parts. Therefore, the total cost, time, and money of installing a clamp-on meter is very affordable. Clamp-on meters are commonly used for application in which leakage is a concern since there is no pipe penetration. Last, no required maintenance is needed with a clamp-on meter, especially with the use of solid coupling available today. Now that we understand ultrasound, how ultrasound is created, the methods of ultrasonic measurement, and the advantages of clamp-on flow measurement, let's go through some real-life application examples. Example number one was a large United States federal agency was mandated to reduce the amount of energy consumption in their buildings. Before you can reduce your energy consumption, you must first accurately measure, which was a significant problem due to the existing flow meter technology originally installed. The existing technology was not consistently measuring accuracy. It was never truly trusted by the customer. Periodic calibration was continuously required, which costed both time and money, as they did not feel they could ever rely on the measurement. GE was able to come in with a PT-878 portable ultrasonic flow meter to spot check and validate the expected flow measurement at multiple locations without shutting down the process. After reviewing alternative flow meter technologies, the customer realized to replace their existing permanent flow meters. They selected the GE Digital Flow DF868 clamp-on meter with temperature inputs and internal energy calculations for their buildings. The final selection was based on a wide measurement range, reduced overall installation and maintenance costs, and no additional pressure drop caused by the instrumentation. Another example is a large Midwestern United States university was having problems with their cooling system. On hot days, they were not able to consistently cool all of their buildings. It was vital to examine how much each building was consuming so they can make improvements to their overall system. These improvements would provide energy efficiencies, lowering long-term capital expenses. They would also keep the residents of the buildings cool and comfortable. The university selected the AT868 Clamp-on Ultrasonic flow meter since it was less invasive. This meant they did not have to shut down the process to install the meter and allowed them to achieve consistent and accurate cooling across the campus. In the end, over 60 meters were installed and quickly identified several areas of overuse and leakage. By addressing these inefficiencies, they were able to improve and optimize their cooling systems. Example number 3 is a Northeast United States university that wanted to improve its infrastructure by renovating and adding several buildings and dormitories. However, the campus had its own central plant, and planners questioned whether the existing underground steam pipelines had enough capacity to support expansion. The university's energy management office decided to review its steam plant for the next 3 to 10 years, and part of the analysis would require steam flow measurement at locations where no flow measurement existed today. GE was contacted to review the steam flow requirements and to offer a non-intrusive flow measurement. GE was able to provide a flow survey using our trained field service team members to address their concerns. Over the span of 2 years, the GE team monitored multiple steam lines with the GC868 Clamp-on Ultrasonic meter and data logged the values for customer review. By using Clamp-on technology, the university was able to obtain the critical information they needed to account for additional development costs for the campus expansion without disrupting service. Another example is a major medical company in Canada. They acquired a large campus and was very concerned about the energy costs associated with their new acquisition. To resolve their problem, they purchased DF868 Clamp-on energy meters and AT868 Clamp-on water meters to monitor, track, and trend usage of their chilled water and condensate. Based on the data that they received, the company made modifications and changes to their buildings and realized energy cost savings and expect more savings in the coming years. Another example is a large hydroelectric power plant in the northwest United States. This customer would earn tax credits from the government if they operated their turbine at peak efficiency. A flow measurement was critical data for obtaining operational efficiency. The customer selected GE's DF868 permanent ultrasonic flow meter due to the customer's great experience with General Electric equipment. However, to reduce the customer's initial concerns, the difficult flow measurement due to the installation location, GE installed a portable PT878 ultrasonic flow meter. With the use of a magnetic clamping fixture and CRS transducers, we were able to overcome the challenging logistics of the measurement and validate the expected flow measurement quickly. Once the measurement was validated, the customer moved forward with the DF868 installation. In the end, the customer did earn the additional tax credit thanks to Clamp-on ultrasonic technology. The last example is with an oil company in operation in the extreme conditions of the Sahara Desert. The application was for gas injection into oil field wells to maintain a constant wellhead pressure for oil production. Unfortunately, the orifice plates and the permanently installed ultrasonic meters were measuring 20% off from each other. In this installation, orifice plates were used at each specific well to control the injected gas. The permanent wetted ultrasonic meters were used at the plant outlet due to existing problems with their original orifice plates and due to the high pressure and large size of the pipe. GE was called to help resolve the flow measurement discrepancies between the orifice plates and the permanently installed ultrasonic meters. The instrumentation engineer wanted to know if a portable clamp-on meter could be used to resolve the flow measurement issues on a heavy pipe wall with high pressure. GE was able to validate the flow measurement at both the 4-inch orifice plate lines and the 10-inch permanent ultrasonic lines. In the end, the PT878GC portable ultrasonic gas clamp-on meter was able to validate that both the orifice plates and permanent ultrasonic meters were measuring the actual volumetric measurements as intended. It was deduced that difference in standardized volumetric flow rate was caused by incorrect application of compressibility in high-pressure natural gas. A portable ultrasonic clamp-on meter was able to resolve the customer's problem, and balance of operation was achieved. Thank you for attending this webinar on clamp-on ultrasonic flow measurement. I hope you learned a little bit more today on ultrasonic flow measurement, and clamp-on flow measurement, but most importantly, how our customers have benefited from these technologies. If at any time you have questions, please feel free to contact me by email or find out more information from our website or LinkedIn page. At this point, if you have any questions, please use the chat feature on your computer.